Welcome back to the Deep Dive. Today, we are strapping in for a bit of a high-speed journey. We're looking at an object that, well, according to the universe's own internal statistics, it probably shouldn't even exist.
That's putting it mildly. Yeah, we're tracking 3IATLAS or C2025N1. If you want the full designation, it's the third interstellar object we've confirmed screaming through our solar system.
Right.
But this one, it's turning out to be radically different from Oumuamua and Borisov, just completely different.
Our sources, they keep calling this thing a major anomaly.
Hmm.
So our mission today is to figure out why. We need to unpack its, extreme speed and sheer size, the stuff that's basically broken our statistical models, and then dig into the frankly bizarre chemistry the James Webb Space Telescope picked up. It suggests, well, a world unlike any comet we've ever studied.
And it's forcing astronomers to fundamentally rewrite their understanding of what actually travels between the stars. This isn't just some, interesting comet passing by.
Right.
It's a really crucial data point. It challenges decades of assumptions about how volatile ices, like water ice, can even survive these incredibly long journeys across the galaxy. And the sheer number of these massive rogue bodies out there, we're dealing with a cosmic giant, really.
Okay, so let's start with the basics, how it arrived. 3IATLAS. It was spotted by the ATLS survey system back on July 1st, 2025. And right away, its speed just screamed, Interstellar.
Oh, yeah, it's a true hypervelocity traveler. When it hit the inner solar system, it was already doing 58 kilometers per second relative to the sun. Hyperbolic excess velocity, that's the term.
58 kilometers per second. That's just jaw-dropping speed. For context, 2I Borisov, our last big interstellar visitor, that came in around 32 kilometers per second.
Right.
This is nearly twice as fast,
Yeah.
carrying way more energy.
Exactly. And its orbital path confirms this, super energetic trajectory. We look at orbital eccentricity, basically how straight its path is. Anything over 1 means it's unbound, leaving us forever.
And this
3IATLS clocks in at 6.14, which is enormous. It just tells us this object is on a very, very straight shot through our system. Definitely not sticking around.
So it's fast, passing through. It makes its closest pass to the sun perihelion. That's October 29th, 2025, somewhere between Earth and Mars orbit. But crucially, the sources are clear. No threat to Earth. Closest it gets is about 1.8 AU in December.
Correct. No danger there. But, the velocity is impressive, sure, but the mass, that's the real headline here.
Yeah, this is where the numbers just sort of stop making sense. They estimate it's anomalously massive, weighing in around, 33 billion tons?
33 billion tons, yeah. And the estimated nucleus size, the solid core, is maybe 5.6 kilometers, about 3.5 miles across. It's staggering.
Okay, 33 billion tons. So why is that anomalous?
Well, this is the insight that fundamentally breaks the existing models. See, we model how planetary systems scatter material out into the galaxy, creating this population of interstellar objects, right? Based on those models, there should be an inverse relationship between size and how often we find them.
Meaning we should find loads of tiny ones first, like cosmic pebbles.
Yeah.
Before we find a big one.
Exactly right. Oumuamua, remember that one. It was 3 to 5 orders of magnitude less massive than 3IATLAS. Tiny in comparison.
Wow.
Our statistics predicted we should have found tens, maybe hundreds of thousands of smaller Oumuamua-sized things before we were statistically likely to just stumble upon something this enormous.
So finding a 5.6 kilometer body this early on, it's like winning the lottery backwards. Statistical improbability.
It really is. It stunned the astronomical community. The implication isn't just, oh, it's big.
Right.
The implication is that the total amount of mass, the budget of interstellar objects floating between the stars, has to be far, far greater than we ever imagined. Our models must be fundamentally flawed.
The statistical models just don't account for giants like this appearing so soon.
They don't. The sheer statistical weight of this one object forces a reevaluation of the whole population distribution. It actually changes our estimates of the mass density in the galactic plane. It's that significant.
Okay, beyond its size, what about its age? Where does a rock this huge and fast actually come from?
Well, based on tracing its trajectory backward, one strong hypothesis suggests it might have originated way out in the Milky Way's thick disk.
The thick disk. That's old stars, right?
Very old. If that holds true, this comet could easily be at least 7 billion years old, maybe older.
7 billion years. That's
That's
older than Earth. Older than our entire solar system.
It makes you feel a bit young, doesn't it? We're hosting this ancient galactic wanderer that's seen more history than our entire planet.
All right, so its speed confirms it's from outside, its mass confirms it's a huge outlier. But the real mystery, it seems, only starts when we look at the weird chemistry it brought along. It clearly acts like a comet dusty coma tail.
Yep. Classic cometary activity. But even its outgassing, the stuff boiling off, is telling a strange story. It's shedding mass like crazy, about 150 kilograms every second.
Whoa.
But its non-gravitational acceleration, that tiny push it gets from the gas escaping, like a weak jet engine, it's remarkably small, less than 15 meters per day squared.
So wait, it's losing tons of gas, but barely moving from that thrust because the nucleus itself is just so incredibly massive.
That's the key confirmation right there. Its huge mass resists that acceleration change. But the real breakthrough on what exactly is escaping came from the James Webb Space Telescope, JWST.
JWST. What did it see back in August?
It looked straight at the gas cloud, the coma, and found a composition that's basically backwards compared to our own solar system comets.
Backwards how? I read it was unusually rich in carbon dioxide, CO2.
Exactly. Unusually rich is an understatement. JWST detected this really strong, narrow peak of gas phase CO2 emission, and alongside that, much weaker signals of water vapor H2O and carbon monoxide, CO.
Weaker water. Usually water's the main thing, isn't it? What was the ratio?
Some sources are reporting an extreme ratio, like 8 parts CO2 for every 1 part water.
8 to 1. At the distance it was observed, like 3 or 4 AU from the sun.
Wrong.
Water should be the dominant gas boiling off, right? Not CO2.
That's what we normally see in solar system comets at that distance, yes. This high ratio is unprecedented out there.
So does this mean it formed in a much, much colder place than our solar system? A different kind of protoplanetary disk?
It certainly points to a different chemical environment, yeah. But the prevailing theory right now is actually kind of interesting. It suggests the nucleus temperature itself might be lower than typical comets out there.
Lower temperature. How?
Possibly due to a dense, maybe insulating crust on the surface. Think of it like a blanket.
A cosmic ice cube wrapped in a blanket. Okay.
Pretty much. See, CO2 ice is much more volatile than water ice. It turns to gas more easily. The theory is this thick crust might be stopping the sun's heat from getting deep enough to sublimate the less volatile water ice effectively.
Ah, so the crust acts like an insulator, keeping the water ice frozen deeper inside, leaving only the super volatile CO2 near the surface to dominate the outgassing we see.
That seems to be the leading idea. It's effectively shielding the water ice. So this object isn't just a giant. Its chemistry looks unique, partly because it might have preserved its internal water ice really well, forcing us to see the CO2 signature that we normally wouldn't expect to be so strong at this distance.
Fascinating. But it is still a comet. It has the right stuff.
Oh yeah, definitely classified as a comet. Despite the CO2 being dominant, JWST did confirm other standard cometary materials are there. Things like cyanide gas, CN, even atomic nickel vapor. It has the right ingredients, you could say, just mixed in very different proportions.
Okay, so given its, crazy speed, its statistically impossible size, and now this really weird chemistry, it was kind of inevitable that speculation would start flying, wasn't it? We have to touch on the theory floated by some researchers, Avi Loeb being the most prominent name, suggesting 3IATLAS could be artificial, similar to the debate we had around Oumuamua.
Yeah, that speculation popped up early on, citing the highly anomalous nature, the size, the trajectory, especially before we had all the detailed chemical data back from Webb. That prompted the artificial origin hypothesis for some.
But let's be clear, the overwhelming scientific consensus, NASA, the broader research community, they're pretty firm on its classification, right?
Oh, absolutely. The scientific evidence points overwhelmingly towards a natural body. Tom Statler from NASA put it pretty bluntly, saying, it looks like a comet. It does comet things. The evidence is overwhelmingly pointing to this object being a natural body. It's a comet.
Can't get much clearer than that.
And the confirmed presence of those cometary compounds, CO, CO2, water, nickel, CN, that strongly backs up the natural cometary classification.
So unlike maybe some of the lingering questions around Oumuamua, in this case, the chemical smoking gun seems to have pretty much settled it for most researchers.
It really has. Even those who initially pushed the alien tech idea have sort of acknowledged the scientific reality. Loeb himself described thinking about it as an interesting exercise and pedagogical, while agreeing the most likely outcome is that it's completely natural.
But regardless of whether it's natural or not, its sheer uniqueness, the mass, the chemistry, makes it a massive scientific priority, right?
Yeah.
We need to gather as much data as possible before it flies out of reach.
Exactly. And that's why the scientific community is really mobilizing. There are active proposals right now to use missions we already have out there in space.
Like what?
Well, things like the Mars fleet, all those spacecraft orbiting Mars, and potentially even the Juno spacecraft, which is way out at Jupiter, the idea is to try and get observations of the comet as it passes through their neighborhoods.
Opportunistic science, using what we've already got deployed.
Precisely. Every single data point helps us figure out what this thing is made of and what it tells us about the rest of the galaxy it came from. These observations from different angles, maybe seeing the side facing away from the sun, that could be really crucial.
Okay, just to quickly give you a sense of the bigger picture, what else is happening in space right now while we track this interstellar visitor? Let's check in on the International Space Station, end of September, early October 2025.
Right, so Expedition 73 crew, NASA, JXA, Roscosmos, astronauts, they were continuing work up there, even with that brief U.S. government shutdown causing some logistical ripples down here. Science doesn't stop.
What kind of science were they focused on?
Some interesting experiments mentioned, one called SHRIMP, not actual shrimp. It's about removing humidity efficiently, vital for future deep space missions. Another, Heat Transfer Host 2, looking at how condensation works differently in space, and the Advanced Space Experiment Processor 4, which is actually trying to manufacture medicines in microgravity.
Manufacturing drugs in space.
Yeah, cool.
And back down on Earth, closer to home.
Well, fittingly, just recently, October 4th was International Observe the Moon Night, a big public outreach event. And it was just ahead of the full harvest supermoon on October 6th.
Ah, the supermoon. So for people who are out observing, what were some recommended things to look for in the moon?
Yeah, the guide suggested looking for the terminator, that sharp shadow line moving across the surface really makes craters pop. Also, Mare Nubium, the Sea of Clouds, that big dark patch, and the Montes Jura mountain range, which catches the light just right sometimes to create the golden handle effect.
The golden handle, I've seen pictures of that. It's beautiful.
It is. And also looking for those bright ejecta rays, the streaks of material blasted out from young craters like Tycho. Really spectacular through even a small telescope. Hashtag outro.
Okay, so let's bring it back and wrap up this deep dive into 3IATLAS. When we boil it all down, what's the lasting takeaway from this?
Well, this truly massive, ancient, and chemically weird visitor from another star system. I think the core takeaway is that 3IATLAS is definitive proof that planetary systems eject massive bodies, not just tiny fragments like Oumuamua suggested might be common, but it's doing so in this really bizarre CO2-rich package that just completely defies our current statistical predictions.
So it confirms the idea that systems throw stuff out, but the scale of what they throw out,
Yeah.
that needs rethinking.
Exactly. It confirms theories about planetary migration and ejection, sure, but the sheer scale demands an immediate rewrite of the science textbooks when it comes to the population of material drifting through the galaxy.
And the observations, they're not done yet, are they?
Oh, far from it. Hubble is scheduled to take a look in November 2025 using ultraviolet spectroscopy to really map out its gas emissions precisely. And JWST is lined up for another round of observations in December as the object is heading out.
And looking further ahead.
Well, new instruments coming online soon, especially the Vera C. Rubin Observatory. That's expected to find potentially thousands of new interstellar objects in the coming years. That huge flood of data will finally tell us if 3IATLAS is just a complete statistical freak of nature, or if it's merely the first confirmed member of a whole new class of massive interstellar visitors we never knew existed.
Which brings us nicely to our final provocative thought for you, the listener. We spent a lot of time talking about the statistical improbability of finding an object like 3IATLAS, this massive natural body, so early in our search.
Right.
So think about that statistical rarity for a moment, and now apply it to the search for extraterrestrial intelligence, SETI.
There's new research out suggesting that for just one other technological civilization to exist in the entire Milky Way galaxy at the same time as us, that civilization would likely need to have survived for at least 280,000 years. A very long time. And even if one exists, the closest one might be something like 33,000 light years away. So here's the thought. If finding a massive natural interstellar comet like 3IATLAS is already statistically improbable based on our current understanding, how much more extraordinary, how much more statistically impossible would the evidence need to be to confidently confirm an artificial object from another civilization? It really highlights the profound rarity that complex life, whether it's just a giant comet or actual technology, might represent in the sheer vastness of the cosmos.
Something profound to think about next time you look up at the night sky, realizing even the natural travelers out there can defy belief. Until next time on The Deep Dive.